Welcome to the Deep Dive, where we cut through the noise of complex research and give you the essential insights. Today, we're tackling a really fascinating new paper. It could fundamentally change how we train large language models, LLMs, how we get them to think. We're talking about making these powerful AIs far better at reasoning, especially when they're faced with tough problems, like, say, advanced mathematics.
Exactly. That's a major hurdle right now.
The paper is called SRFT, a single-stage method with supervised and reinforcement fine-tuning for reasoning, and it comes from Yuqian and their team. Our mission today is basically to unpack how this approach unifies two major LLM training methods, supervised fine-tuning, which we'll call SFT, and reinforcement learning, or RL.
Right, the two big ones.
Essentially, it's about making LLMs smarter, not just better at, retrieving information. Think of this deep dive as your shortcut to understanding the cutting edge of LLM fine-tuning. All right, let's start at the beginning. Before we jump into SRFT itself, we really need to understand the two big players here, SFT and RL. What exactly are they, and why has combining them effectively been, well, such a puzzle?
Okay. So supervised fine-tuning, SFT, that's probably the most common way we adapt these models after their initial training. Imagine you have a huge set of questions with perfect answers, input-output pairs. With SFT, you basically show the model these examples over and over, and it learns to mimic them. It adjusts its internal parameters to increase the probability of generating those specific, correct outputs.
So it's like learning directly from a perfect textbook, distilling that knowledge.
Exactly. That's a great analogy. It's all about learning from existing, high-quality data.
Okay, got it. So what about RL reinforcement learning?
Right. RL is a completely different beast. Instead of being shown the right answer, the LLM learns by doing. By trial and error.
Like training a dog.
With treats. Sort of, yeah. The model generates a sequence of words, maybe trying to solve that math problem, and then it gets a reward signal based on how good that sequence was. Did it get the final answer right? That might be your reward of 1, otherwise 0.
Okay.
But the big challenge here is often what we call sparse and delayed reward.
Ah, right. You mentioned that.
Yeah. Imagine teaching that dog a really long, complex trick, but you only give it the treat right at the very end if it did the whole thing perfectly.
It would have no idea which part it got right or wrong along the way.
Precisely. That's what LLMs face. They get this score, this reward, only after generating a potentially long chain of reasoning. It's incredibly hard to figure out which specific choices, which words generated earlier led to the good or bad outcome.
Makes sense.
There are algorithms to help, like one called GRPO Group Relative Policy Optimization. It helps the model compare its different attempts and figure out the relative goodness, which is clever, but the core challenge remains.
So we have these two powerful learning styles. SFT learns from examples, RL learns by doing. Traditionally, people applied them one after the other, right? First SFT, then RL.
That's been the standard sequence, yeah.
But if they're both so powerful, why isn't it as simple as just doing one than the other? What are the actual headaches when you try that sequential approach?
That's really the core dilemma researchers have been grappling with. SFT alone, it can sometimes lead to models that just memorize patterns.
Rote learning.
Exactly. They might reproduce the answers from the training data really well, but without truly understanding why that answer is correct. So they might struggle with new unseen problems. That's overfitting.
Okay. And RL?
RL, on the other hand, while it's great for pushing performance on complex tasks, has its own issues. It can be very sample inefficient.
Meaning it needs tons of trial and error.
Yeah, a huge amount. It has to explore this vast space of possible word sequences, and it can take a long time to stumble upon good solutions. Sometimes it gets stuck in a rut, too.
How so?
It might repeatedly generate similar, but ultimately suboptimal answers. We call that mode collapse. It's like it finds one okay-ish way to do something and just keeps doing that, failing to explore better possibilities.
Like a student stuck on one wrong approach to a math problem?
Precisely. So the main challenge has been finding the sweet spot. How do you get SFT's broad knowledge and RL's focused optimization to work together without these downsides?
And this isn't a brand new problem, right? This is part of a longer story. Can you give us a quick sense of how LLM reasoning has kind of evolved to get us here?
Sure. I mean, the fundamental ideas of reinforcement learning for decision-making go back quite a ways, maybe key theoretical work over a decade ago. But specifically for LLMs and reasoning, things really heated up in the early 2020s. We saw crucial benchmarks emerge, like the math dataset and models like Minerva.
These were designed to test math skills specifically.
Exactly. They provided really tough problems that forced models to actually reason, not just pattern match. These datasets were indispensable. Then came technical advances, things like more efficient ways to manage the huge memory these models need, which actually made complex RL training feasible. And by 2024, things really took off. New, even harder math data sets like Numina Math and Olympiad Bench appeared. Algorithms like GRPO became more refined.
And better base models too, I imagine.
Definitely. Models like Qwen 2.5 Math 7b provided stronger starting points. And we saw this explosion of research, specifically applying RL to reasoning tasks. It's been a huge focus in the last year or so.
That timeline really puts it in perspective. It's been a rapid acceleration. So let's dive into the SRFT paper itself now. They use this really striking analogy I liked. SFT as a sledgehammer and RL as a scalpel. What exactly do they mean by that? How do these methods actually change the LLM?
Yeah, it's a great way to visualize it. It's about how they impact the LLM's policy, essentially. Its internal strategy for picking the next word. SFT, the sledgehammer, makes these broad, coarse-grained global changes. It basically pushes probabilities around across the board, increases the likelihood of words it saw in the good examples, decreases others.
So big, sweeping adjustments.
Right. It reshapes the whole probability landscape, often making the model's output more deterministic, more confident, based on those examples.
And the scalpel, RL.
RL, the scalpel, makes fine-grained selective modifications. It's much more precise. It tends to adjust the probabilities for only a small number of words, often the ones where the model was initially most uncertain.
The high entropy ones.
Exactly, the high entropy tokens. It leaves a lot of the existing structure, like numbers or standard proof phrases in math, relatively untouched. The paper even shows visualizations, confirming this SFT causes big shifts. RL makes tiny targeted tweaks.
So sledgehammer versus scalpel. How do these very different modification styles affect the model's overall learning trajectory, the learning dynamics?
Well, their analysis showed that SFT causes much larger changes from the original base model's policy. If you just use SFT, it generally performs well because it strongly guides the model towards those demonstration patterns.
It pulls it hard towards the examples.
Pretty much. RL, while it also improves performance, tends to operate much closer to its starting point. The changes are more constrained, more localized in the probability space. It fine-tunes rather than overhauls.
Okay. And where does this idea of entropy fit in? The paper calls it a critical indicator of training effectiveness. What does that mean here?
So entropy in this context is basically a measure of the model's uncertainty. High entropy means it's unsure, spreading its bets across many possible next words. Low entropy means it's very confident, very decisive about the next word.
Got it.
The key insight is how entropy changes during training with these different methods. Pure RL tends to cause entropy to drop very quickly. The model rapidly becomes very certain, very deterministic in its outputs.
Which sounds good, right? More confident.
You'd think so, but it can be a double-edged sword. This rapid drop in entropy can actually reduce the model's plasticity.
Its ability to keep learning.
Exactly. It becomes less adaptable. And this is where the sequential problem really shows up. If you try to apply SFT after this RL phase where entropy is plummeted, you can actually see a sudden increase in entropy again, and performance tanks. It suggests a kind of fundamental incompatibility if you do RL first. The RL locks the model in, makes it resistant to the broad changes SFT tries to impose.
Wow, okay. And SFT alone?
SFT alone shows a different pattern. Maybe a brief initial entropy increase, but then a steady, sustained decrease as it learns the patterns, leading to performance gains. So how entropy behaves is a really crucial signal.
This really highlights the challenge. Given these starkly different impacts, especially on entropy and plasticity, it makes sense why just sticking them together sequentially would be problematic.
Right. The paper points out two major issues with sequential approaches. First, the RL then SFT order just seems to consistently underperform. The RL phase kind of hardens the model too much.
We're trying to reshape hardened clay.
Good analogy. And second, the more common SFT than RL approach.
Yeah.
Well, the RL phase can sometimes trigger catastrophic forgetting.
Forgetting what it learned in SFT.
Yeah, it can temporarily lose some of the knowledge or patterns it picked up during the initial SFT phase. Performance can actually dip when you start the RL training.
Why would that happen?
The authors suggest it might be because even good SFT datasets might contain some slightly imperfect or suboptimal steps in the reasoning. Pure RL, when applied sequentially, might struggle to distinguish those or efficiently leverage the good parts of the demonstrations.
So all these problems with sequential training really motivate their approach.
Exactly. It pushes towards needing a way to integrate them simultaneously, right from the start.
Okay, so if sequential is out, what is the SRFT solution? How does it actually pull off this single-stage unification without the downsides?
The core idea of SRFT is this simultaneous optimization. Instead of step 1, SFT, step 2, RL, it blends the objectives together in a single training loop. It learns directly from both the expert demonstrations, those high-quality examples, and from self-exploration rollouts. Responses generated by the LLM itself during training. It tries to solve a problem, gets a reward, and learns from that attempt whether it was good or bad. SRFT does both concurrently.
Like learning from the textbook and trying homework problems at the same time, getting feedback on both.
Precisely. And it uses both types of information directly in its optimization process.
And how does that crucial entropy measure get used in this unified approach? You said it was key.
Ah, yes. This is where the entropy-aware weighting mechanisms come in. This is really clever. SRFT dynamically adjusts how much weight it gives to the SFT part and the RL part, based on the model's current entropy, its uncertainty.
So it adapts the learning based on how confident the model is.
Exactly. For the SFT component, learning from the expert demonstrations, there's a weight, WSFT. This weight actually reduces the influence of the SFT loss when the model's entropy is high when it's very uncertain.
Why reduce it then?
To prevent the model from being pulled too strongly by demonstrations that might not perfectly align with its current, still developing internal state, it avoids confusion when the model is unsure.
Okay, makes sense.
Then, for the positive samples generated during its own RL-style exploration, there's a different weight, WRL. This one works to kind of prop up the entropy, preventing it from dropping too low too fast.
So it encourages continued exploration.
Right. It helps maintain diversity and stops the model from becoming overly deterministic and getting stuck before it's found really good solutions. It's constantly balancing learning proven paths with exploring new ones, guided by its own uncertainty.
Wow, that is quite sophisticated. So it's managing this balance act constantly.
Precisely. And how it uses the demonstrations is also interesting. It employs a dual strategy. First, it uses the standard SFT loss for that coarse-grained learning from examples. But second, it also feeds those expert demonstrations directly into the RL batch. This is treated like an off-policy update, boosting the perceived reward or advantage for those successful paths, encouraging the model to explore directions similar to the expert.
So it leverages the demos in two different ways.
Yes. And for the self-exploration part, the RL objective is split. There's a part for reinforcing the positive, correct rollouts the model generates itself, structured similarly to SFT but using its own successful attempts. And there's a part for penalizing the negative, incorrect rollouts.
So reinforcing good attempts, discouraging bad ones.
Exactly. And all these different pieces, the weighted SFT, the demonstration-boosted RL, the positive and negative rollout handling, are combined into a single unified loss function that SRFT optimizes throughout training.
That sounds incredibly elegant, weaving everything together. But the proof is in the pudding, right? How did it actually perform in their experiments?
Right, the results. They were quite compelling. They used a strong base model, Quinn 2.5 Math 7B, and trained it on a dataset called OpenR1 Math 46K 8192.
That's the one generated by another EO?
Yeah, containing about 46,000 math problems with high-quality reasoning steps generated by DeepSeek R1. They used a simple reward, 1 for correct, 0 for incorrect, building on that GRPO algorithm.
Okay, and the tests?
They evaluated it rigorously. 5 in-distribution math benchmarks, things like AMC Math 500, which are similar in style to the training data, and crucially, 3 out-of-distribution benchmarks, RSEC, GPQAD, MMLU Pro. These test if the model can generalize its reasoning skills to totally different types of problems and domains.
That generalization part is key. So what were the numbers? How did SRFT do?
On the core mathematical reasoning tasks, SRFT achieved an average accuracy of 59.1%.
And how does that compare?
It's a significant jump. It beat methods using 0RL by 9.0%. It outperformed standard SFT methods by 4.8%. And importantly, it even beat other sequential SFT than RL methods by 3.4%.
So that single-stage unification really paid off.
It clearly seems so, at least on these tasks.
Okay, better at math reasoning. But what about that crucial generalization? Could it apply what it learned to new areas?
Yes, and that was another strong point. On those out-of-distribution tests, SRFT also came out on top, scoring an average of 62.5%. That was 4.7% better than the best baseline method they compared against.
That's really encouraging. It suggests it's not just memorizing math tricks, but building more robust reasoning.
That's the interpretation, yes.
Right.
It seems to build more transferable reasoning capabilities.
Were there any other interesting observations from the training itself beyond the final scores?
Definitely. They noted that SRFT showed faster performance improvements during training. And tying back to our earlier discussion, it maintained more stable entropy compared to pure RL.
So it avoided that rapid drop and stayed more adaptable.
Exactly. It suggests the policy could continue exploring effectively throughout training. They also saw something interesting, a progressive lengthening of responses.
The model wrote more.
Yeah, over the course of training, its solutions tended to become more detailed, more thorough, showing more steps in its reasoning, rather than just spitting out a short answer. That's often seen as a good sign of deeper processing.
More detailed reasoning, stable entropy. It sounds promising. Did they specifically test how important those entropy-aware weights were? The SFT and RL?
They did. They ran an ablation study, which is standard practice, that basically trained versions of SRT with each key component removed to see the impact.
Yeah.
Removing the SFT weighting, SFT, caused performance to drop by 4.0 percentage points. Removing the RL weighting, RL, led to a 2.9-point decrease.
So quite significant drops.
Absolutely. It confirms that both of those entropy-aware mechanisms are critical. They aren't just fancy additions. They are essential for achieving that stable training and the superior final performance.
Okay, so bringing it all together then, SRFT really looks like a powerful new way forward for fine-tuning LLMs, especially for these complex reasoning tasks, by merging SFT and RL in this unified entropy-aware way.
Indeed. It seems by really understanding and actively managing the model's uncertainty, its entropy, SRFT finds a way to get the best of both worlds. The broad knowledge from demonstrations and the precise exploratory power of RL all working together. And that strong performance, particularly on the generalization tasks, is really promising for making LLMs more useful beyond just their specific training data.
But as always in research, it's never the final word. What are the current limitations here? Where does this research go next?
Right. The authors acknowledge that, while effective, their current use of entropy dynamics is relatively simple. Future work could explore more sophisticated techniques, maybe adaptive entropy scheduling, changing how entropy is managed over time, or looking at it on multiple timescales.
Getting even smarter about managing that uncertainty.
Exactly. Another point is that the current method relies on having access to those high-quality expert demonstrations.
Which might not always be available or easy to get.
Precisely. So future research could investigate how to adapt SRFT to work effectively, even with imperfect or noisy demonstrations. Making it more robust to real-world, messier data would definitely increase its applicability.
That makes a lot of sense.
Yeah.
Well, it's fascinating. The journey towards genuinely intelligent LLMs clearly continues, and SRFT seems like a really significant step in making them not just knowledgeable, but actually capable reasoners. This whole deep dive really highlights how crucial these fine-tuning strategies are becoming. It really makes you wonder, if we can get this effective at teaching math reasoning, what other complex domains could benefit from this kind of unified learning? Legal analysis, scientific hypothesis generation, the possibilities seem vast.
It certainly opens up exciting avenues.
Thank you for joining us on the deep dive.